In this video, we'll take a look at part 3 of the application problems, and the subject is optimization. This is something that you'll be doing in the calculus classes, not using graphing or Desmos, but you'll be using calculus to find maximums and relative minimums. So there are many real-life applications that can be modeled using polynomials. Calculus topics include optimization problems where a maximum or minimum value must be found. For example, business, there's a maximum profit or a minimum cost. Engineering might be a maximum load of a beam. Biology might want to find the maximum population. In the two problems below, we're going to be working in a packaging company that creates different size containers for customers. So the first application, we're going to create an open box from a rectangular piece of cardboard that has the greatest volume possible. So we're maximizing volume. To make an open box, you cut squares of size X from each corner of the cardboard and fold the edges up to make a box. If we start with a rectangular piece of cardboard that's 10 inches by 14 inches, find the side length of the square we should cut from each corner and also find the maximum volume. So notice when you take and cut X out of each corner, then the height of your box is going to be X. And that's what's going to vary. 10 inches is the length of the side, but if you cut X out of each, then what's going to be left as the side of your box is 10 minus 2X. Then if the width of your box or cardboard is 14 inches and you cut X out of each corner, then the width when you fold the box up is going to be 14 minus 2X. So the first thing I'd like you to do is use X values and find the volume for each different X value. So you have to remember the formula for the volume of a box is equal to length times width times height. So as you're cutting out a side length of 1, so when X equals 1, I'll go through one of these with you and you can fill out the rest. If X equals 1, then 10 minus 2X was 10 minus 2, which is 8. 14 minus 2X, 14 minus 2 times 1 is 12. So the volume of your box is 1 times 8 times 12. So 12 times 8 is 96. So the volume of your box would be 96. This is in inches, cubic inches. So try it for the other values. If X equals 2, we'll do one more together. When X equals 2, then we get 10 minus 2 times 2. 10 minus 4 is 6. 14 minus 2 times 2. 14 minus 4 is 10. So the volume of your box would be 2 times 6 times 10. So that would be 120 cubic inches. So notice the volume got bigger. So follow the same process to figure out what the volume of the box would be to see if you can see a pattern. So you want to answer the questions, what happens to the volume of the box as your X values increase? Then write an expression in terms of X for each dimension of the box. I've done that up above. And then write the formula for finding the volume of a box in terms of X. Then, what is the domain of your function? What values of X result in a physical box? So you have to think a little bit. X can't be just anything. What values can X be in the cardboard, physical cardboard, so that you can still actually make a box out of the cardboard? Once you get your function, graph it in Desmos. Make sure that your domain is what you selected, and make sure that it shows, not a complete graph, but it shows the values that make sense on the domain that you chose. And then copy and paste. Again, you can take a screenshot or you can use the snip tool. Then you're going to find the zeros of your function using algebra, both exact and to the nearest tenth. In this case, you're going to have exact values, no nearest tenth. and then explain what the zeros represent in terms of the side length and volume of the box. Then you'll find the maximum. You're going to use Desmos to do this and explain what that maximum represents. So you're going to end up graphing a polynomial, a cubic polynomial, and then identifying from your cubic the features of the box. All right, I hope that gives enough hints for the first application. The second problem is minimizing surface area. A company wants to manufacture cylindrical aluminum cans with a volume of 1,000 cubic centimeters, which is a liter. What should the radius and height of the can be to minimize the amount of aluminum used? So we want to make sure that the can holds 1,000 cubic centimeters, but we want to use as little material as possible. So in this case, we need to know what the formula for surface area of a cylinder is. Surface area is 2 pi r squared, those are the two circles added together, plus 2 pi rh. If we were to cut the can and unfold that rectangle, it would be the circumference of the circle times the height. That's where that formula comes from. The volume of a cylinder is pi times r squared times h. So number one is going to lead you through how to find the equation to be minimized. And it's a little tricky because we're given the volume and asked to minimize surface area. So follow the steps to find a formula in terms of a single variable r. So first you're going to substitute 1,000 in for v in the formula. Then you're going to solve that for h. That means you're going to divide both sides by pi r squared. So you have that the height equals 1,000 over pi r squared. Then substitute your expression for h above into the surface area formula. So we're going to end up with surface area equals 2 pi r squared plus 2 pi r times h, but use what your h is above, 1,000 divided by pi r squared. Okay, from there you can simplify your expression. Your pi's will cancel, your r's will cancel. Then you're going to graph this in Desmos, and a hint, use the window, get provided, copy and paste your graph, and then use Desmos to find the minimum value. Once you find the radius, which is what your formula is, once you find the radius, answer the question, what radius should the cylinder have to minimize the surface area? And then substitute it in your height formula to figure out what height the cylinder should be to minimize surface area.